again, so we had this fact that I just erased, that every compact group is a real form of something, and now we're proving the term that every reductive group has a compact real form and is essentially unique. And as I said, again, I want to emphasize this because it's quite a shock to me that there is no good proof of that without structure theory. So I think that we can plug into the machine G and get the dual of the category. Actually, I'm not sure here. Maybe this is a general nonsense proof that works, and I'm just too confused to realize it. I can look at the category of representation of a given reductive group G. It satisfies all the axioms that Krein needs in order for the Krein duality theorem that I mentioned before. So it looks like the category theory of a compact group. So there is a compact group associated to it. This is exactly the group automorphism of the forgetting factor. And our group G must be the group of complexification of that one.
Did I understand correctly that what you said now is that you start with this complex G, you take TG, which is a compact group?
Yes, exactly.
At this point?
Yes, and I'm looking at the complexification of this compact group, and it is naturally a subgroup. It's more a priori of the group I started with. This would be a natural thing, but they will have the same category theory, so they will have to be the same. Now I'm not sure. I'm too confused. I was confused over a week and about it, whether this general nonsense proof works or not.
But what is missing? That this compact group, we also know that the compact group is algebraic.
The compact group is just
the TG.
Start with GC. Okay? Take the category of representations, algebraic representation of it. Take the forgetful functor for vector spaces and take the T of it, the automorphism of the forgetful functor that commutes with tensor product and the direct sum and conjugation. This would be a compact group. Okay, now one needs to prove that this is a compact group. I don't know a priori that this, I mean, what we did is not correct. I don't know a priori that this is that is a category of representation of a compact group. So I cannot use this omission thing. So actually, I think this is the problem. I think this is why this general does not work. So I didn't state Krein theorem correctly. Yes, in the statement of Krein, I mean, what are the groups that actually are group representation of a compact group? There is something about complex conjugation, which you don't, a structure that you don't see just looking at the category of representation of that algebraic group. Okay, so which right now I don't remember how to state this exactly. I'm saying that this general nonsense proof as is does not work. Maybe there is a way to fix it.
But maybe it's not even true. T of G.
This theorem says that it is no.
But wait a second. TG is embedded as. So TG will be compact?
Yes, yet we don't know it if we just run the proof as I say. We need to verify an extra axiom, which is kind of come up with a compatible real structure on all these vector spaces. Oh yeah, in Krein theorem, it's not representation on arbitrary vector spaces, but on Hilbert spaces. You need a real structure, or you need some.
But what confuses me is you always have a map from G to TG, so you have a map from the complex.
No, you don't have a map from G to GG. Oh, sorry,
From
GC. Sorry.
You mean G is now our GZ. Let's say G is the complex reductive group,
Yes.
and now you build T of it.
Yes.
But you always have a map from G to TG.
No, because
Not in
the
injection.
elements in G do
Not
not.
an injection, but you have a map.
No, they don't. They don't.
What do you mean now? You just
Oh, yes.
Yes.
Yeah, you always have a map.
Forget it.
Yeah, not a map. Is it truly a map?
Yes. Okay. Excuse me. Let me go. What I said here was erase the video. I was putting myself into this loop a few times during this the last week, so I don't know why I do it in front of you now. So let me start by proving the theorem by cases. Let's start with the easiest case. Case. G is a connected dose. Remember, now we are over the complexes, the complex numbers. So there's no splitness, etc. That means G is up to points C star today. Then I want to come up for you with a compact Zariski dense subgroup. And you do it for me?
S1 to the.
So you can take S1 and K is S1 to them. Well, S1 is tools. I mean, topological tools in C star. Okay. So this is one case. Now, the second case will already be non-trivial. G0 is a tools. So G does not need to be connected anymore. Now I want to prove that I can find a compact dense sum in it, and so how G like? G is like there is a G0 here, and modulo it we have a finite group. Give the name L. Now the picture, find the K, right? Color it. And so what is K? Not instead of finding K, I already know some K prime in it. And actually, by the way, this is a canonical characteristic subgroup of that one. It's the unique compact in it. This is characteristic. So it will be normal inside G. And so now I will have G mod K here. Now let's look at G mod K prime. This is K prime here. Now what is this piece here? C star mod S1 is R star. No, it's not R star. It's R star plus. If you take log, this is just the additive group of the rings. So I'm claiming that this is this in here. Is an extension. It has Rn. This is the R star plus piece coming from C star to the N. Inside, maybe I call it E, because this is an extension problem that I'm trying to solve now. And here we have, if I divide by Rn, after dividing by S1 to the N, I'm getting this F here, right?
So K prime times that is not.
Yeah, my answer, now we're solving a question, right? We are looking for K, which is compact and dense inside G. We have K prime dense inside G0, but modulo the group generated, the risky closure of K prime will be G0, and modulo it we have F. We have the connected components of my group. And I want K to include K prime, but also to be projected on F here, right? So I want to find a finite group, a compact group, in E that will project on F, and its pre-image in G, of course, will be a K prime extension of this compact group, and it will be my desired K. Am I clear? I'm saying something very, very simple, but somehow everything I said is slightly too complicated. What I want now to solve is this extension problem. Can I view F as a subgroup of E? So let's repeat again. So it's inside G, I have this torus group. Modulo it, I have a group which is a finite by Euclidean. And if there is a subgroup, finite subgroup in this group E, which falls onto F, then this subgroup in E, what? Okay, this is why we got confused. What is it? I'm taking the pre-image of E inside G will be the K prime extension of F. It will be a group in which K prime is a finite index. It will be K will be pi inverse of maybe this is S of F. Is compact if I can find such an S. And then is this clear?
I'm confused about the E is the quotient here?
Yes.
Of G by K prime.
E is G by K prime. I don't know
Why is this contained in Rn?
K prime is S1 to the n inside C star to the n, which is my G0. And K prime, as I said, it's characteristic, it sits as a normal subgroup of G. G mod K prime, maybe G0 mod K prime, I claim first of all that it's R star plus C star mod S1 is R star plus to the n, which I identified via log with Rn, the additive group of vector space. Okay? G mod K prime, this is a group I'm calling E, and so this is the definition, and so since G0 is cofinite in G, then also modulo K prime, the image of G0 will be cofinite in the image of G. So Rn in E is cofinite. Right, F here is E modulo Rn. And if, again, I'm asking, if this is Rn, maybe I should, now this is E act on this, E act on itself by conjugation. This is normal, so this is stable under conjugation. So E act on Rn by conjugation, but Rn is a billion. So it's in the kernel of this action. So the E action on Rn by conjugation splits or factor through the projection to F. F act on Rn by conjugation.
What does the abelianity of Rn has to do with the triviality of conjugation by E?
No. E act, again, E acts on Rn by conjugation?
Yes.
Okay. In particular, this subgroup itself acts on Rn by conjugation?
Yes.
And I claim it acts trivially, because this is because Rn is abelian, and this is why the action factors through F. So F acts on Rn, and I may form, this is a fair, here is a group, and fixing this action of F on Rn, I may form this, and I may ask, this in color, I may ask, is it the same? This question is the same as asking, let's put it in brown as well, do I have such a lift homomorphism of, I mean, this is the map that takes that F to that F. Here. So this is my question. And I'm claiming that this is, if this is the case, then I could view F as, so this tends to be denoted S just to be compatible with that notation. Then I could view F as a subgroup of E, a finite subgroup of E. E is a quotient by K prime. And its pre-image will be a compact subgroup of G. And this compact subgroup must be Zariski dense, I claim. Why? Its Zariski closure certainly will contain G0. Already K prime is Zariski closure of it contains G0. And modulo G0, it hit everything. Right? So that question written here is everything which is left. And this question could be phrased by as a cohomological question. So question. So I don't know if all of us know this formulation is H2 FRN 0. For every finite group F and a linear representation F to G and R. So Rn is an F module. F actually by automorphism of the additive group Rn. Now we know from linear algebra that every automorphism of Rn has an additive group. So maybe not from linear algebra, from group theory or something. That every automorphism of Rn is actually linear. And H2 exactly measures in that case the class of extensions up to isomorphism of extensions, and up to isomorphism of extension, and the trivial element of H2 is that extension. Is a split. Maybe I'll be explicit about it, just because for me this is like bread and butter. Oh, who didn't see it? Okay, I'll explain this. So fix any lift from F, call it psi, to E. Okay? So this is not a homomorphism. And consider basically now I can ask how much non-homomorphism is it. If it was a homomorphism, then this expression, if psi was an homomorphism, then this expression was trivial. Now, this
You
expression,
intentionally have one minus one in, one minus out.
now, because if you think about it, if you project this expression down to f, it will be trivial. On E, it is not a homomorphism. But when I project back, so this is a section, right? This is here I have pi, so pi psi is the identity of f. It's not the S, it's not the section, the homomorphism that S there was a homomorphism. So I used a different letter. But of course, in F, this is trivial, which means that this is in Rn. So F is a function from F times F to Rn. And now you can, it has some special properties. So it is rather easy to see that it is, which is a 2%. So actually, the way it goes, if it was trivial as a cosine, if it was a co-boundary, so there will be some h, then f would be a boundary of some function of one element. Now, there are computations that I'm not doing, but if it is a boundary, then f is the boundary of h is a function from f to e, and then I would, and then computation, which will tell you that if I define Sx, age is the fixed, is how to fix, is a way to fix psi, is a homomorphism. So this is general nonsense of algebra. And this I cannot.
Yeah. You can see it.
Okay. And now, so what is
Yeah, well,
yes?
sorry again. Why is it 2 cosine?
So this is a computation that I didn't do. It's like
You're restricted to what? I mean, you define it
so
over f times f, that's okay.
so I can define E is what as a set. E is Rn times f, right?
Yeah.
As a set, and using psi, you can redefine the computation and the multiplication here. I mean E as multiplication.
Okay.
So I guess this multiplication is by psi. Right? Every element in E as a representative, a cosine G in E, I can write down as psi of pi of G times something phi of G, which is something from Rn, right? I mean, these two, this is pi G is the image in F, and psi of pi G is something with the same image at F as G, so these two differ by something from the kernel. So, so this phi is the projection on the Rn copy, and this is the projection on the F copy. So using psi, I made an identification here.
But these are set.
This is a set term, right? But this guy has a product structure in it. So there is a product structure on this, which one can write down explicitly. I will not do it right now.
Okay.
And this product is associative. And when you write down the associativity, we get that this psi must.
Oh, in order for that.
Oh, sorry. well, this f, I mean, psi and f must satisfy a certain relation, which is called two cycle. Two cycle is exactly what encodes
No, that I know, but
associativity.
so that's the step you skipped.
This is the step I skipped.
Okay.
And yeah, because this is very standard. So I'm just again exposing this. What I'm trying to say. Where am I? Okay, so I want to show. So again, so if this cocycle that I'm getting, I will get a cocycle. If this cocycle is a boundary, again, you compute and see that using this co-boundary, you can twist the original psi, and it will actually be a homomorphism. Okay? So this is why, again, this classical thing, if this will split if and only if this cohomology class is 0. And the claim is, so here's a fact, so a theorem if you wish, f finite then actually for every n, hn frn is 0, and Roman explained to me the easy proof at the break.
It's the same n. It's the same n.
No. This is no. And we'll see what it comes here. So basically, what is this guy? So in order to see it, the easiest way to see it is to take again, we forget all about the extension problem. By chance, our problem, the extension problem is vanishing of some cohomology, but now we look in cohomology theory, and we have all maps from. Now I'm reminding you how to think about these guys. So this is the cohomology associated with some complex. So what is this complex? A. So you look at all maps.
P is equal to
F, K, R, N. So I'm having F, K plus 1, R, N. I'm having such a complex. This is the spaces of all maps of this form. And now if you compute the cohomology of this complex, remember, this is complex because if you go twice, and I'm not writing down the standard boundary operators, but these are really standard, and if you go twice, this is 0. So this is the complex. And now once you have complex, you can ask, how cyclic is it? So what happens if I take the kernel of this, modulo the image of that one, and this would be the cohomology. And if I would compute the cohomology of that one, what will I get? Hmm?
HK.
No.
Maybe it's fair to say, what is the K cohomology? Which position is it in that case? Because here you have the homogeneous resolution. And here you look at the
This is the homogeneous. So this is the space of all f to the k points in Rn, and okay, maybe I don't want to give a crash course on cohomology.
But since you wrote this thing on the board, just remind me, what is C of FK? What's this?
This is all maps. Let's see here just because sometimes you want to confuse. I don't know. All maps
From FK to Rn.
from Fk to Rn. And when I'm having also, yeah.
And And that's the k minus 1 position in the complex.
This one, this k position, and once you have, this is the homogeneous resolution. Once you have a function, sorry, when you have a function of from f to the k, and you want to cook a new function for f to the k plus 1, you can just forget a component. But of course you have several ways to do it, k plus 1 ways to do it, so you sum in an alternative way. And this would be the boundary map. So this is standard boundary map. Now, but if you just look at this complex, and this is again a standard thing, its cohomology is trivial. There is nothing going on here. Actually, I didn't use the f action in any case. F was just s set. It can't measure anything. So this will give me a trivial, but actually, so cohomology is the derived functor of the invariance. This is the fancy way to call it. So I'm taking this complex and I'm applying invariance to it. And invariance is I want functions now which are f invariant when f acts diagonally on the base, on the source. So I'm applying f everywhere, and now if I take, so this is still a complex. This is something that remains true when applying a functor. Now we can compute the cohomology of this complex, and this is a meaningful thing, and this says something about f, and this is exactly that guy. This is the general nonsense of homological algebra, and okay. Well, and here there was nothing special about the coefficients, the representation space of f. So here is what Romans told me to do. If I have now, f was the name of my cross cycle, f in here, I want to show that this is trivial. So if I forget about invariant, if I just think about it as a function, which is an f invariant by chance, but who cares about that, then there will be, since then I know that the cohomology is trivial, then there will be a function here that that f is, there will be h in here, that f, or maybe h prime, is the h. Because f, I mean, it's a function that goes to 0 here. I'm talking cross cycles, it must come from, it must be an image here. But the problem is that the h prime need not be f invariant. But the thing is that I can average this h prime up, and here I'm using a property of the coefficients problem. That we have convexity properties here. So I can average this guy and make it invariant, and it will have the same image. So the averaging will be some h. And this will be dh when h is something from here. So this explains why this is always 0, at least if I can go backward.
So whenever the thing, the Rn is replaced by a vector space over the rationals, then
It works the same. If your group
is finite,
or if the characteristic of the group is not, I don't know, I mean the order of the group and the characteristic of the field don't match.
Then, I mean, this is, you're talking about positive cohomology, or additive.
This is group cohomology.
The cohomology is usually.
but how could it be that this is
But
so
it's
complicated?
I don't know.
Look at
You have to do all this just for the case
Well, I
of,
mean-
for the case of
Yes, as far as I know, yes, this is for the case of finite groups. But, I mean, the problem here is with non-connected groups. I mean, actually, it's much more complicated, but maybe a bit more standard if I talk about semi-simple groups, which I will talk in a minute. This is way more complicated. So, as I said, this is a hard theorem. And this is not the hard part yet. But okay, so this proves this function, and this proves that this extension is trivial, and this, and everything, and we are done with this example. Next case. Okay, remember where are we? we are discussing cases of that theorem. We did a trivial case here. We did a next case here. I want you to remember not just what we did, I mean that case, but not just that we proved this case, but also the method. I will come back to it again. And the next case, I will state that the theorem, or this is a semi-theorem. So it's
a semi-simple theorem.
the semi-simple theorem. Yes, it's the same as theorem. I mean, but now for connected semi-simple group. So these are the three cases. Now, next thing I will do this. So I postpone the proof of that one. So this is the main case, and I will prove our semi-theorem in that theorem. Okay, question?
Why is it dense? I mean,
Why is K dense?
yeah.
Okay, I do you agree that K, even K prime, is dense in G0? Okay, so I just need to show that it is dense modulo G0. It's actually
So
on.
it's in any concept.
Okay, so I need to prove the semi-theorem, but first I will prove the implication. I will prove the theorem, modulo it, and I'll say about the semi-theorem. I will use Lie algebra in order to prove it, and structure theory of Lie algebra, semi-simple Lie algebras, root systems, etc. Okay, so it's all will go there eventually. But now we're still in algebraic groups, and we want to assume that. We want to prove the general case. So before proving it, let me make a claim.
The 1 minute to go on that.
Oh, really? Okay, so maybe I'll amuse you otherwise. In this 1 minute, I will say something about meaningless, about something that we can
That
just
is important.
not that important, and we will do it next time, including time. But so many you have questions. Comments.
More of a question. So just to see that I get it, if you take F instead of to be finite to be some amenable groups, this argument still works?
If it will be compact. Amenable is not good enough because the image is not need not be compact.
Okay.
Right? But yeah, so just if F was compact, the same, and of course you need continuous cohomology here, so the same argument works. You can average with respect to the Haar measure instead of with respect to the Haar measure, and counting measure, and now if I knew that the image is bounded, it will also work for amenable group. So this is what we call bounded continuous cohomology. If F is amenable, then this is 0. This is the fact. And of course, for finite or compact groups, the cohomology are bounded. All cocycles are bounded in any case.
So, since I don't know nothing about nothing regarding cohomology, when you connected between that lifting question and the vanishing of the second cohomology, you had this exercise of showing that this is a 2 cocycle.
Yes.
And then,
Which is a standard, again.
which is a standard to check, okay, I get it, but then you must work with a certain definition of what is your, how did you get your cohomology, whatever it is. and then you go and choose yourself your favorite, most convenient
Yes, yeah,
chain complex and show me a vanishing of a completely different cohomology.
So actually,
And
to be precise,
What's going on here? Is it always the case that no matter what you do, you get the same cohomology? Or?
so first of all, this is not arbitrary cohomology. If you do the checking here, there are two. Okay, first of all, in cohomology, the beauty of this science is that you can juggle between many other models.
Mm-hmm.
But actually, if you want to compute group cohomology, there are two best models, computing ones, called the Bader solution, the homogeneous and inhomogeneous ones. And then basically, I can, instead of taking F invariance here as I described, I could just average with respect to the first coordinate here and rewrite things without this F here. But then, and I will get function spaces depending maybe on other coordinates. Just a minute. Then the boundary maps will be different. There is another way of writing the same thing. And if I would write down explicitly the F's that I got here, I said that if you write down and get a 2 cocycle, it will be explicitly a 2 cocycle in the bound in the inhomogeneous cohomology, which actually it's not really, you don't need to go through everything in order to apply this. I mean, I could have solved this for you in one or two boards of computations. It is easy.
To show that it vanishes, or
To show that it vanishes. Instead of saying cohomology, I don't need to say cohomology. I can write down a formula for F, or I can. I pick psi here. I can write down F explicitly here. I can write down explicitly. It is easy to do a functional equation which it satisfies without calling it a 2 cocycle of whatever version. I can come up using F and some averaging technique. I can come up with an H, not explain why I did what I did, and I can just look at this expression and prove using the 2 cocycle property of F. I can use that this guy here is a homomorphism. I can go through that without saying the word cohomology, but then it would be a miracle, right? While
So,
true miracle,
let me, you answered my question, but let me rephrase it again. What I'm asking is if it's a complicated thing or just a simple standard thing, that all of these cohomologies are the same.
It's one of the very basics, very steps in a very complicated theory. So there is this beautiful and very powerful theory called cohomology, theory of groups and other things, which is worth studying, and it has many applications. And the fact that you can do things in a model-free way is remarkable. And we have an expert here. And these are the very basics. And the fact that H2 corresponds to extensions, I mean, those things are actually, this was known, and this computation were known way before people developed the general theorem. But nowadays, it is unavailable too, which is a shame not to know.
Shame on you.
No, I don't know it as much as I would like to.
That's why I said shame on you.